Okay, we've already looked at alcohols and carboxylic acid structures. Now we're going to look at their intermolecular forces with water and with each other. So if we look at alcohols to start with, we can see that alcohols have a dipole. If you look at the fact that the oxygen is negative and the hydrogen is positive, this creates a net dipole on this end of the molecule, with the positive end being down here. And this interacts with water's dipoles, which are present because of the same reason, because hydrogen and oxygen have such different electronegativities. If we look at the way it interacts with hydrogen bonding, we have even more strength in the interactions here, so about 1/10 the strength of a covalent bond. And this is possible because oxygen is part of the NOF group, and therefore we have such a difference in electronegativities that the electron density is pulled entirely off the hydrogen to create a very polar hydrogen, and this forms a hydrogen bond, which is shown in green here, which means that the solubility of alcohol in water is very high. Now, if we look at the boiling points of different alcohols, we can see that as the number of carbons increases, the boiling point goes up, and the hydrogen bonding here remains the same, or is very similar at least, whereas the dispersion forces will be increasing, and this increases the boiling point. If we compare alcohols and their non-polar cousins, the alkanes, you can see that there's a big difference in boiling point, and that's because of H bonding. So hydrogen bonding means that the energy required to break the molecules apart to turn it into a gas is much higher than with alkanes. But you can see alkanes follow the similar pattern of dispersion forces increasing the boiling point as you increase the number of carbons. If we move on to carboxylic acid, which are similar in the fact that they have an OH group, but they also now have a carbonyl group here, and then this is just attached to an alkyl group there. That means it's very polar, so you've got a very negative end there and a very negative bit there. And that creates more hydrogen bonding again. So that means that alcohols actually have a lower boiling point than carboxylic acids, because carboxylic acids have such strong interactions with water. So if we just look at that occurring, we can see that we've got hydrogen bonding between the carbonyl group and the water there, but also we've got hydrogen bonding between the OH group and the water. Now, as we increase the size of the carboxylic acid, if we look at this homologous series here, we are increasing the size of this part of the molecule with more and more carbons. It gets less and less soluble. And the reason for that is because it gets less polar. The part of the molecule that is increasing in size is getting larger and larger, and this part is largely non-polar. This is the non-polar end of the molecule. And therefore, because water is a polar solvent, and polar solvents like to dissolve polar molecules, they're able to dissolve polar molecules, it means that as this is getting bigger and bigger and less polar, it becomes less soluble in water. So you can see that happening here, gradually losing solubility. If there is no water present, the hydrogen bonding between carboxylic acids also occurs, forming what we call a dimer. So this is when there's no water around, it's able to actually form two hydrogen bonds between both ends there, which increases the boiling point of carboxylic acid again.